Adding a methyl group to propane, or a propyl group, we get C4H10, which is called butane. And so in this video, we're going to look at butane, we're going to look at butyl compounds, and we're going to look at conformational analysis. Now, notice in the title, I actually say butanes and not butane. And the reason for this is because when you add that fourth carbon, you can, the fourth methyl group, you can add it in one of two ways. So if I add a methyl group to a propyl group, then I get a straight chain, and it's called butane. And I can represent the bond line formula like this. But notice when we were talking about propyl substituents, there was a propyl substituent, there was an isopropyl substituent. If X in isopropyl group is a methyl group, it looks like this. So this is still C4H10. It is still a butane. It is called isobutane. So we have butane and isobutane. And isobutane in the bond line formula is drawn like this, and we say it is a branched alkane. A branched alkane because we actually have a straight 3-carbon chain, and coming off of that, branching off of that, is a methyl group. So when we have straight chains, we call these unbranched alkanes. We have branched alkanes and unbranched alkanes. Now, let's look at the three-dimensional representation, our dash and wedge representation. We can draw it like this, just like we drew that of propane, right? Of course, now we're adding another methyl group to this. So this is butane, not isobutane, but butane. And one of the things that, one of the cool features about butane is thinking about its conformational analysis. Why? Well, if we look down this particular carbon here, that second carbon here, so now, we're getting to a point where we have to think about labeling our carbon. So if I label the carbon at the end, 1, and then 2, 3, 4, I'm going to cite right down that C2, C3 sigma axis. Now, when I do that, how does the Newman projection, what does the Newman projection look like? Well, again, my front carbon is C2. So what's attached to my front carbon other than C3, because I'm looking down that C2, C3 axis? Well, I have 2 hydrogens connected to it, and then I have C1, which is a methyl group. And I can represent that like this. So I have a methyl group, and I have 2 hydrogens. If I'm looking in that orientation, my methyl group is going to be pointing up, and the 2 hydrogens are going to be down and to the left and right. Then I have to look at C3, and what is attached to C3? Well, 2 hydrogens are going to be on the top, left and right, and then there's C4 that's also attached, and C4 is a methyl group. And so I get this conformation. For butane, this particular conformation has the 2 methyl groups 180 degrees from one another, and we call this conformation the anti-conformation. So let's look and see what happens as we rotate a complete 360 degrees, what every individual structure looks like, because now we're getting a little bit more complicated. So we start with our anti-conformation, staggered, right? We still have a staggered conformation where the 2 methyl groups are anti to one another. Now, I'm going to rotate 60 degrees. And I'm going to do this in again, a clockwise fashion. Remember, I'm holding the front carbon stationary. So the orientation of the substituents on the front carbon never change. And it makes it easy because now I can draw that front carbon, I can draw the substituents on that front carbon, and I know that they're never going to change. And all I really have to worry about is what's happening to the back carbon. As I rotate clockwise, the hydrogen goes up, the hydrogen on the left rotates up behind the methyl group. The hydrogen on the right rotates down behind the hydrogen, and the methyl group moves, again clockwise to my left, to behind the hydrogen. And we call this a hydrogen methyl eclipse because the hydrogens, or the methyl groups, are eclipsed to two hydrogens. Okay, so we rotate 60 degrees again clockwise, so we're moving the methyl group now up, and again that front carbon stays the same, so there's that blue methyl with the two hydrogens. My green methyl group is now rotated up, and the hydrogens follow suit. So now I have a staggered conformation. So notice my first was staggered, then I go to eclipsed, now I go to staggered. But this staggered is different than the staggered anti-conformation. The two methyl groups are getting very close to one another. They are 60 degrees from one another. We call this gauche. When two alkyl groups, two methyl groups, are 60 degrees from one another, that is a gauche conformation. And the reason for this distinguishing feature is because now we have to start thinking about steric effects. And as a matter of fact, there's a little bit of steric effects that go into play in this gauche conformation relative to the anti-conformation, where the two methyl groups are 180 degrees from one another. So we're going to rotate again at 60 degrees. Now the methyl groups are going to come in line. So again, I'm going to draw the front carbon the same way. Now I have the green methyl that's eclipsed with the blue methyl, and the two hydrogens are eclipsed with the other two hydrogens. We call this a methyl-methyl eclipse. So again, this conformation is different than the hydrogen methyl eclipse because now I have two methyl groups that are in very close proximity, and we're going to see there's some steric strain that's associated with those two methyl groups being so close to one another. Again, we're going to rotate 60 degrees. So now my methyl group, my green methyl group, is going to go on the right-hand side. And again, we have a gauche conformation. Then we're going to rotate another 60 degrees, right? So now the methyl group is going to come down, and I get this conformation, another eclipse conformation. But if you notice, this is very similar to the first eclipse conformation we had, right? Because I have both methyl groups eclipsed to hydrogens, and then I have a hydrogen-hydrogen eclipsed bond. And so we'll simply distinguish this as the H, hydrogen methyl group eclipsed. Notice I can rotate one more time and I get back to my original staggered anti-conformation, and then the thing's going to go round and round again, right? So this is what we're talking about, and now we have various eclipse and staggered conformations that don't have the same energy associated with them. What does the energy diagram look like? Well, if I start with the staggered anti-conformation, it has the lowest energy possible. And I rotate 60 degrees to get to my hydrogen methyl eclipsed conformation, right? And so now I move toward the gauche. So as I go away from eclipsed and into staggered, I lower the energy. So understand, always when I go from staggered conformation to eclipsed conformation, eclipsed conformations are higher in energy. Then I move to a staggered. It becomes lower in energy. But notice The energy isn't the same for my anti-staggered, the first conformation, and my gauche staggered, that second staggered conformation. There's a little bit of energy difference of 0.6 kilocalories, and this deals with the methyl-methyl steric strain, just a little bit of steric strain. So now when I go from that gauche to my eclipsed, it's a methyl-methyl eclipsed, and it is the highest in energy because of the methyl-methyl steric strain, right? So that is my methyl-methyl eclipsed. And when I move back down, now I get into the gauche staggered conformation, which has the same potential energy as my first one. Then I go back to eclipsed of the hydrogen methyl, right? And then eventually return to my anti-staggered conformation. And we see that the energy difference between the staggered and the hydrogen methyl eclipsed is actually very similar to that of the eclipsed of propane. It's 3.4 kilocalories per mole. Now, the energy difference between my anti-staggered and the methyl-methyl eclipsed is 1 kilocalorie per mole higher. And so that has to do with the two methyl groups that are sterically clashing with one another, right? So the energy is 4.4 kilocalories, or 1 kilocalorie per mole higher in energy than a hydrogen methyl eclipsed. And so you see, now we're getting this, this potential energy diagram that isn't just a simple oscillation, but there are slight variations in energy as we rotate about the carbon-carbon bond. And as a matter of fact, the more strain there is, the harder it is to overcome that rotational barrier. And so alkanes tend to reside in what we call a minimum conformation. And most of the time that is an anti-staggered conformation. And so we get these staggered anti-carbon-carbon bonds, right? All right, so let's take a look at butyl compounds, right? C4H9X compounds. And notice when we are talking about butyl compounds, we have to talk about both isomers, both butane and isobutane. And we have to look to see whether or not the hydrogens are equivalent with one another. So with butane, we see that there are two different types of hydrogens. We have two methyl groups at the end. We have two methylene groups in the middle. And those methylene groups happen to be equivalent because of this, there's symmetry involved, and they happen to be connected to the same substituents. So we have a methyl hydrogen, HA, and a methylene type of hydrogen, HB. When we replace HA, right, we simply get this. And we call these butyl compounds. So butyl alcohol, butyl amine, butyl chloride, butyl bromide. However, when we replace HB with a substituent, we get this. Now, it is not isobutyl because we already have isobutane. This is referred to as sec-butyl, and I'll tell you why in just a little bit. But for now, just recognize it's called sec-butyl compound. So sec-butyl alcohol if it was an OH, sec-butylamine, sec-butyl bromide, right? Now let's take a look at isobutane. Isobutane also has two different carbons. The methyl groups, so there are three methyl groups, and then that CH group. That's called a methine. We'll talk about that later on. But suffice to say, I have then three, the methyl hydrogens, HA, and the methine hydrogen, HB. If I replace HA with X, I get isobutyl X. So this is where isobutyl is carried over. So isobutyl alcohol, isobutyl chloride, isobutyl bromide. When I replace HB with X, then I get this structure right here. And we call this tert butyl compound, tert butyl alcohol, tert butyl bromide. Now, where do we get the sec-butyl and the tert butyl designation? Well, in order to understand those designations, we have to understand the classification of carbons. So we have really 4 different classifications. We have a primary carbon, which we often abbreviate 1 with the degree. So whenever you see 1 and a degree, that means a primary carbon. Now a primary carbon is a carbon that is attached to one other carbon. It may be attached to another substituent like an OH group or a halogen, but if it's attached to one other carbon, then that particular carbon is called a primary carbon. Then you have a secondary carbon, which is abbreviated 2 with the degree symbol. And a secondary carbon is attached to 2 other carbons. Then we have a tertiary carbon, which is abbreviated 3 with that degree, and a tertiary carbon is attached to 3 other carbons. Lastly, we have a quaternary carbon, and I'll talk about that later on, which is attached to 4 carbons, right? So there are no hydrogens on it, basically. All right, so notice secondary and tertiary, if we abbreviate those, sec and tert, that's where we get sec-butyl and tert-butyl, because the substituents in sec-butyl are coming off of a secondary carbon, and the substituent of tert-butyl is coming off, and you can see this on this slide here, you can see that the substituent is coming off of a carbon that has 3 other carbons attached to it. And so hence the name tert-butyl compound.